Hello, this video is a last minute video, so sorry for the low quality. It's about this large number. I hope it will be published in time to integrate the Mega Fave Numbers playlist. So, why this number? Well, because it satisfies this equality. You might think, so what? Nothing amazing with that. And you'll be right. In fact, I'm cheating a little bit. I would like to talk about a concept I called main basis of integers. And this pair of half mega numbers is the right entry point. Unfortunately, they are too small, but their sum is not. It's bigger than 1 million. So, what is the main base of an integer? Starting with an example is always a good idea. Here is one. 1, 2, 3, 4. When you see this, you probably read 1234. But if you are a programmer, you might think it's a double byte number written in hexadecimal meaning. Let's put here the base as a reminder and calculate that. 1 times 16 cubed plus 2 times 16 squared plus 3 times 16 plus 4, that is 4,660. But it also could be a number in octal, or in base 6, or in base 4. Hey, wait a minute. Base 4 is not possible because in base 4 we only can use the first 4 digits that are the 0, the 1, the 2, and the 3. 1, 2, 3, 4 only makes sense if it's read in base 5 or bigger. The smallest value that 1, 2, 3, 4 can represent is 194. That's the key point. In any finite sequence of digits, there is a larger one, which imposes what is the smallest base in which a sequence can actually represent a number. Now, we can define what a main base is. An integer b is a main base of n if the expansion of n in base b contains the largest digit possible, that is b minus 1. That means this representation makes no sense for all smaller base than b. Equivalently, numbers that have the same representation in any base are greater than n. From our previous example, we observe that 5 is a main base of 194 since its writing in base b contains the digit 4. And it's the same for the base 10 because the 9. In fact, this number has 13 main bases, which are here. In the following, we call beta the function which gives the number of main bases of each integer. So beta of 194 is 13. Since 0 is O in any base, and O is never the largest digit possible, it follows that beta of 0 is 0. Beta of 1 is 1, beta of 2 is 2, beta of 3 is 2, beta of 4 is 2 again, then beta of 5 is 3, and so on. If we plot this function, we get that. Very chaotic, isn't it? N is just a single digit n in any base greater than n. So n plus 1 is always the main base of n, and there is none beyond. So beta of n is always smaller than n. Moreover, 2 is the main base for all non-zero integers, because all of them start with a 1 in binar. So beta of n is greater than 2. In fact, we can prove this lower bound, because n is n plus 1 minus 1. So if b divides n plus 1, then the last digit of n in base b is b minus 1, and b is the main base of n. 1 cannot be a main base, but it's always a divisor of n plus 1. So, removing it, we get beta of n always greater than the number of divisors of n plus 1 minus 1. If beta of n is small, we can expect n plus 1 to be a prime number. Let's check that. when looking for numbers that have only two main bases, we find 2, 3, 4, 10, 36, 40, 82, 256, and then none. For numbers which have only three main bases, well, there are these ones. And finally, hey, well, two big numbers are there. On increasing both of them by 1, we get a pair of twin primes. They are the last ones, I guess. In fact, I think it exists a constant lower than 3, such that the number of integers having k main bases is equivalent to c to the power k. This is a bold conjecture, knowing that I have no idea how to prove that these sets are finite, not even for true. If someone seeing this video has an idea, he is welcome. I hope you enjoyed this video. If you like numbers, on big numbers, you can check the Mega Fave Numbers playlist.